All right, I think we'll get this started. Hello, everyone. My name is Laura Snyder. I am the Manager of Science Communications for the National Center for Atmospheric Research, and I'm really excited to welcome you to our tutorials today about what COVID-19 can teach us about atmospheric science and vice versa. You are in the first tutorial where we're going to look at the intersections between climate and COVID. And I also want to apologize because our director, Everett Joseph, could not be here today. He was very excited. He really wanted to be here, and a conflict came up that he could not get out of. But I wanted to pass on some of the things I think he would want you to know, which is that NCAR has been around for 60 years. We were founded in 1960. And from the very beginning, we've been working on developing atmospheric models. And so as the decades have gone on, they become more complex, more comprehensive, more useful. And they've grown to encompass all kinds of things. So not just the atmosphere, but the atmosphere's interaction with the land, with the ocean, with the influences of the sun, with ice sheets. And all of the models that we create are community models. They're open source and available to researchers across the world. And these days, our community models, we have weather models, we have climate models, we have hydrology models, and models of the sun. Our flagship climate model is called the Community Earth System Model, and it's used around the world. It's a major model that's been part of the IPCC reports. And today I'm excited to introduce you to Dr. Andrew Gettelman, who's been one of the developers of this model and is also an expert in cloud microphysics and a senior scientist here at the National Center for Atmospheric Research. And he's going to lead you through some of the connections between COVID and climate change. Just one housekeeping note before I turn it over to Andrew, which is that if you have questions, please throw them in the Q&A function in the Zoom app, and we'll be keeping an eye on that, and we'll ask as many questions as we can get to at the end of the presentation. All right, Andrew, take it away.
Okay, go ahead and share my screen. So hopefully that works. Can you hear me okay, Laura?
Yes.
Okay. So as Laura said, I'm a climate physicist. I work at the National Center for Atmospheric Research, which is mostly funded by the National Science Foundation. And this is work I also did while I was on sabbatical last year for the beginning part of the pandemic at Oxford University in the UK. So over the last few months, like anyone, and I and my colleagues have been home. We've been listening to the news too much, and we've had some extra time. And like scientists, we get curious. That's our job. So you give us unlimited access to the internet, and interesting things start to happen. So I've been listening to colleagues who look at weather forecasts, who analyze satellite data, who measure cloud drops from aircraft. These are people who can ask what if questions with supercomputers and petabytes of satellite data and have things like electrostatic particle counters lying around their houses. So I've seen and discussed some very interesting intersections between the work we do on climate and weather and the COVID pandemic, and that I'd like to actually share with you today. And so basically, COVID and climate change are two global interconnected crises with evolving science. Obviously, a pandemic is much faster than climate change. I've sort of shaped climate change for people in the last couple of months as saying, it's kind of like that COVID pandemic, but for our grandkids. And the question is, what does a cloud and climate physicist know about pandemics? Well, I don't know much about biology, but it turns out we actually know quite a bit about pandemics, and I'm going to try to talk to you about some of those intersections here today. So first is talking about the physics of clouds, pollution, and what that means for pandemics. Drops of salt water and organics are very similar, or basically what are cloud drops. Well, that's also kind of what comes out of your mouth when you cough, sneeze, or even breathe. And there's some intersections also in that the environment and pollution can affect airborne drops in lungs in particular and human health. And it's actually air pollution and emissions. The other issue is that we know that our lives changed dramatically this year, and that actually had dramatic impacts on air pollution and emission changes that occurred during the lockdowns. And some of that's continued to this day as transport patterns have changed and many people are no longer using city centers or offices. So there's impacts on air pollution and climate change, and there's some effects of emissions changes that we're looking at. These particles, whether they be from the surface or also from aviation and contrails, actually have small effects on climate. And then the other thing is being somebody who's spent a lot of time trying to understand both weather and climate modeling, we think a lot about uncertainty and we think a lot about the future. And there are large uncertainties in modeling pandemics, as we've all understood in the last couple months. And what we know about weather and climate prediction can actually teach us a little bit about uncertainty in epidemiological modeling and vice versa. So I'm going to touch on some of those aspects in the talk today. So let's talk about the physics of clouds, pollution, and viruses in air. The technical term is human phlegm or sputum, and that's basically saltwater and organic molecules that come out of your mouth. That's actually not that different from sea spray, and the dynamics are not that dissimilar from what happens to small cloud drops and aerosols, particularly in marine layers over the ocean. So scientists have spent a lot of time studying this, and what's interesting is that the scientific perspective on that we have from cloud physics is actually different than the scientific perspective that either engineering or biological experts have been looking at when they look at indoor air quality and they look at actually transmission of viruses. So the thing to understand is that viruses are tiny. They're about 1/400th the width of a human hair. It's actually not the size of the drops that the virus that matters, because the virus doesn't come out of your mouth alone. It's always contained in some sort of drop. It's the size of the drops that matter, and that means all of our expertise on understanding what happens to cloud drops and turbulence actually comes into play. And these are groups that haven't really talked scientifically. It's been interesting to watch two different communities come together and try to understand each other in the last couple months for some, obviously a very important and critical societal problem. So there are actually two populations of drops that come out of our mouths. One is very small aerosols. These are about 1/10 of the width of a human hair. That comes out when you're breathing or when you're talking, and it comes out without a high velocity. The large drops are more like the width of a human hair. That's what happens when you cough or sneeze. Now, the interesting thing is the large drops hit the ground quickly, and that they hit the ground typically within about 2 meters. And that's actually, when you hear about a 2 meter or 6 feet social distancing rule, we're really talking about these large drops that come out with sneezing or coughing. It's hard to get any drops to move beyond 2 meters quickly, and it's hard to get the small ones to move very fast. So for example, think about throwing a baseball versus throwing a feather. The lighter drops or the lighter particles, you can't throw very far. You can't push very far. They have too much air resistance. So the other issue is that these large drops tend to hit the ground pretty fast within about 2 meters. Maybe you can get some of these drops 3 to 5 meters. They tend to hit the ground in a couple of seconds to a minute. However, these small drops, if you look at the physics of them, they don't settle very fast. It takes hours. And actually they settle faster, they settle more slowly than just the turbulence in the air would push them around. So they really don't settle at all, and they certainly don't settle within 2 meters. They actually spread. The concentrations will disperse, and in open air, they fall off very, very fast. The other interesting thing that's been known is that the virus is viable in the air for something like on the order of an hour or so. And that's actually somewhat crude the way that's been tested. You basically take aerosols in the air, sample them at different times after emission, and then you have to culture the virus, those particles for a few days to see if the virus actually grows in a petri dish. So it's not exactly an easy test. So what do we actually learn from all this? Well, what this tells us is that these small aerosols remain in enclosed spaces for hours. We don't actually know if the infection happens in big and small drops. This actually matters. We have scientists who have done things like take instruments and that sample sea salt aerosol, pull them off of airplanes, stick them in the lab and cough on them. But we can't really work very well with live virus because we're not really set up for that. And the people working with live virus don't have as sensitive particle size counters as we have. So there's still some work that needs to be done. The virus can last an hour or more in enclosed spaces. And that means, and there's too much dispersion outside to matter. So you can see how this impacts what you would think about and what you would do in a pandemic. The social distancing is based on physics, that these big drops can't rapidly move more than 2 meters, but that may not be the operative issue here. The operative issue may be these small drops that can persist for hours in enclosed spaces, or an hour or so, where they may be viable. So the interesting thing about this, of course, is that masks then reduce transmission. They stop almost all the big drops, and they also limit many or most of the small drops. So they reduce the viral load in air. And again, they reduce it from transmitting from somebody, not just somebody receiving the virus, but the virus actually leaving people's mouths. It also means that there's a lot more these drops when people are talking or people are obviously coughing or sneezing. So symptomatic people will produce more drops, but talking or singing will also produce a lot of drops, more so than if people are not talking and just breathing. So that tells us a lot, and there's a lot of open issues there, but that shows you where a lot of this, the recommendations come from, and they come from some of the basic physics, and we potentially could refine some of these questions with answers like, does the infection happen in big or small drops? I think from a societal perspective, we kind of know it happens from small drops, and it happens when they stick around in the air for a long period of time. There's been some interesting studies on isolated events that actually show that, for example, environments where people were singing or talking, which means things like choir practices or bars, are really good for actually transmitting the disease, even if you're more than 2 meters apart. So the other issue is that the pandemic has had impacts on pollution. Pollution's associated with transport and with industry. And of course, suddenly in March, the transport for people dropped pretty dramatically, and industry was halted during the height of lockdowns. So these are some, sorry, let me just, there we go. Okay. Just trying to make sure I can see what's going on with the chat. It halted, and so this is an image, and you'll see more of this in Gabby's talk, and she'll talk a lot more about the issues with this. But here's an image of basically the particle loading from a satellite over India. So this is sort of the particulate pollution in the air over India, and it shows 2019 and 2020 and the difference between those. And you can clearly see over the Indo-Gangetic Plain, which is this big blue area where there are probably about 300 to 400 million people that live in that area. It's the most heavily populated part of India. There was a big anomaly and a big reduction in the overall particle loading. Now, this can be misleading because there's a couple of different things going on. Obviously, we're looking at 1 month in 2 different years. And as Gabby will talk about, the meteorology can actually have a big impact on air pollution during this period. But there's a lot of evidence around the planet that a lot of these, particularly particle emissions, actually drop pretty substantially. A lot of that was either due to cessation of industry for a month or the sustained reduction in transport. So now I want to move on and talk a little bit about climate and sort of segue into understanding climate change, and then how that actually folds back on pandemic and some of the intersections there, particularly the intersections with uncertainty. So we usually phrase it as climate is what you expect, weather is what you get. So this is a graph that shows the frequency of occurrence, so the higher bars mean higher percent. This is the distribution of all possible minimum temperatures over the 20th century in Madison, Wisconsin. And so what this shows is that the overall climate in Madison, Wisconsin is the distribution. That's the expected minimum temperature on any day in January. But the weather could be any of these particular values. And the all-time coldest temperature in the 20th century in January was January 30th, 1951. You hit a minimum temperature of 40 degrees, minus 40 degrees centigrade. That happens to be about minus 40 degrees Fahrenheit as well. It's really cold. But in any given January, you can be anywhere on this distribution. So weather is the sort of chaotic behavior of where you are in the distribution. Climate is the whole distribution, right? So when we're talking about climate, we're talking about the shape of that curve and how it evolves, for example, or how static it is, or climate change is how that curve evolves. And interesting enough, chaos theory itself was developed by and codified first by a meteorologist named Edward Lorenz in 1961. And he basically came up with a simple model to explain why the weather is not predictable. That's the origin, actually, of chaos theory, is in the weather. So when we talk about climate change, we talk about taking this distribution, say a distribution of temperature, and moving the whole thing around. So if you think about that distribution of temperature, we think of a probability, we think of the mean. The mean climate is basically the expected value, or the most frequent value. Sometimes in a symmetric distribution, it's the most frequent. And when we talk about climate change, we talk about shifting that distribution. So the area under these curves at the tails indicates, let's see, with a laser pointer. The area under these curves represents the probability of getting a temperature higher than this amount. So you have a certain amount of hot weather. If you shift the distribution, all of a sudden the area goes way up. So the probability of getting a given temperature exceedance goes way up, and you'll get some temperatures that we've never seen before. So these are record heat waves, for example. And correspondingly, on the cold side, you actually see the frequency of cold weather go down, and you won't see record cold temperatures as much anymore. It's still possible, but it's not as frequent. So that's what, when we talk about climate change, we talk about shifting this distribution. So what did COVID actually do? It didn't really shift the distribution. I'll get into that in a minute. But it did change the emissions that cause climate change pretty substantially. So this is an interesting plot. It's the change in global energy demand by fuel. And this is estimated by the International Energy Agency. And it was done on April 30th of this year to reflect what was happening with the lockdowns. And each of these is a value of the change every year in each of these electricity, the energy demand by fuel. So you can see coal saw the largest decrease is expected to have the largest decrease in 2020, followed by oil. Actually, sorry, oil has the largest decrease on this scale, then natural gas, then coal, then natural gas. Nuclear also. You'll notice renewable energy actually increased slightly despite the fact that total energy demand went down. And in aggregate, it's expected that this is about something like, I think it's about a 10% reduction in fossil fuel use averaged over the year. During the height of lockdown, when industry was also shut down, it was more like a 20% reduction. So this is a plot of the total emissions, so not showing the change every year. That's on the bottom is the annual change every year. So you can see this is the largest reduction in fossil fuel emissions basically that we've ever seen in amount. And that obviously the only other time emissions have gone down recently was during the Great Recession in 2009. There was a slight drop in emissions. That was the financial crisis you can see here. So here you're seeing the largest drop that we've seen in recent memory. And it's about 20% during a couple of months in the spring, Northern Hemisphere spring. And it amounts to something, I think they're estimating about 8% drop in total fossil fuel emissions over the whole year. And you can see what this does. This brings us back to emissions of what they were about 10 years ago. So it's basically rolling back the clock on fossil fuel emissions by about 10 years. So what's interesting is there's another small climate effect. So that's actually a cooling tendency that's incredibly small. What actually seems to be a larger effect is by clearing the skies and by clearing the air, that actually allows more net energy into the planet. So this is some estimates, preliminary results with NCAR's Earth system model that Laura mentioned at the beginning of the talk. So this is a climate model, and these are experiments that we've been looking at. We've been putting in the drop in aerosol or particle emissions over, and these are 3 different ways of looking at doing simulations. We've been looking at that over the spring, using estimates that other people produced of what actually happened with these emissions, such as those International Energy Agency estimates I showed you, or calibrating them against satellite data showing the reductions in aerosols. And then we actually can simulate what happens to the net energy, and that net energy increases slightly. It leads to a temporary warming of the planet, and it does so because it clears up the skies and it changes how the particles affect cloud properties. So cleaner skies have temporarily warmed the planet. You see that's already recovering. The impacts on surface temperature are extremely slight. It's likely you would only see them in controlled experiments, and they are much smaller than the meteorological variability on any given day, basically. But that's interesting. This offsets, probably more than offsets, any reductions in the fossil fuel use over the short period of say this year. Most of these values, the aerosols will tend to recover probably pretty close to where they were at the beginning of the year. We may be down a little bit because we will still see differences in transport use that have reduced our aerosol production. So this is interesting, and it's good, right? So what's interesting on the lessons for what this means for climate change are actually interesting from a climate change policy view as well. So we stopped 40 to 60% of air travel, most commuting, and 75% of car use during the height of lockdown. Even those fundamental and huge changes to our daily lives resulted in only about a 20% cut in fossil fuel use. Why? Well, we still have an energy system that uses fossil fuels. We still have a food and delivery system that uses fossil fuels. So you can't just shut the planet down and that doesn't solve climate change. And then interestingly enough, this was offset by warming due to reduced pollution, these aerosol and aerosol cloud effects. So what it says about policy measures is we need to evolve our economy, not stop it. It also says that, interestingly enough, that non-essential travel and aviation emissions are not really the main issue, that power plants are probably the major source of fossil fuel emissions today. That if we stop 75%, 60% of our air travel, we really don't see anything happening to fossil fuel emissions globally. There's a couple of other interesting messages. Renewables have held up more than reduction in the more dirty fuels, and particularly things like coal. Part of that was because the fixed sources, these fixed sources from, or these flexible sources from renewables actually are easier to change over time. Or sorry, that's not what I meant to say. Renewables have held up, and the reason the renewables have held up is because they're variable and they're easy to turn on and off, and they're easier to gauge demand with. So the largest reduction was in the dirty fuels, and that was things like coal that are the base load. When the base loads went down, they were turned off and actually not even needed. So the coal and the fossil fuels are becoming more expendable. The coal was actually the first to go. It's interesting that in the United Kingdom, for example, from May, June, and July, they actually shut off all their coal-fired power plants because they didn't need them. And the UK grid was expected to be carbon-free by 2030. They now expect it to be free by carbon-free. They expect it to be coal-free actually next year, based on their experiences this year with managing a grid without the coal. The other nice thing about this, which is the second bullet here under the main messages, is if fixed sources are a major issue, it's easier to change those over time. And these power systems are an example on how coal use is actually declining, will continue to decline. And the pandemic has shown how it may actually be possible to make it decline even faster. And so I think that will actually have long-term positive impacts on doing something about climate change. So let's talk about how we model weather and climate, and then a little bit about how we model viruses. And then I'm going to get into uncertainty and how the uncertainty for both weather and climate and virus modeling works. So the way to think about it, I usually explain how a climate model works, or weather model, which is essentially very similar. I'll explain the differences in a minute, is that it's an accounting exercise constrained by physics. So imagine a spreadsheet, and what I've shown here just happens to be a spreadsheet of dollars. This is some sales for hypothetical sales of a company from some demo for Microsoft Excel. But think of a giant spreadsheet, and at every point in the planet, you have entries for not dollars, but water, heat, wind, salt, carbon, aerosols. All these different things are tracked. And you have a spreadsheet at every grid box on the planet, both in the horizontal and in the vertical. You have different spreadsheets at each point in the atmospheric column. And then you account for all the processes, and you write physical equations that describe how these things will change over time, how energy comes into the system, how water condenses into a cloud, how it falls out of a cloud with precipitation. You then solve these equations for all these processes at every point, and you then have a set of equations for how these points interact. So how the wind blows and how it pushes around all these quantities like heat, carbon, salt, pollution. So, and you basically advance it in time, and you advance it in space, and then you repeat. So it's this giant set of spreadsheets all over the planet that you're just iterating in space and time. Now, the common problem here is it's easy to keep track of the total amount of water or energy in the system, but many of these processes are hard to describe at the right scale, and we have very imperfect representation. So for example, I do a lot of work with cloud physics, and I showed you this picture of a cloud, which is highly detailed, and the different darkness and lightness here indicates that there's different amounts of water content in different parts of the cloud. But if we're running a global climate model, our cloud would look like the picture on the right. We would basically have two different values to describe everything that's going on in this cloud. And then the other problem is understanding the physics of clouds on that scale is actually very difficult, and we actually have to try to fit what we can observe, the picture on the left, to what we can model, which is the picture on the right, and we get a lot of uncertainty. So let's talk a little bit more about how we model viruses. So what you hear a lot about, and what one of the goals of public health is to understand the local virus reproduction rate. So particularly when we're trying to understand the future, you want to know what they call the reproduction rate, or R value. That's the number of people infected for each case of say, COVID-19. Sometimes if you're doing this on an individual basis at different locations, you call it the transmission rate when you're doing modeling at different locations. But this is a critical metric. If each person spreads it to more than one person, you get exponential growth. If you spread it to less than one person, then you get an exponential decay of the virus. So how do we actually come up with these magic numbers? Well, that's the interesting part. This is estimated, actually, as I'll explain, from lag testing data with some adjustments. And this is, there's an interesting little model. It's called Rt.live. It's a simple, as I'll show you, it's a couple of equations. It's a simple model for this reproduction rate. And it's what a lot of the more complex modeling systems use. They build up similar types of equations. They do it in space and time. And they actually have transport between them, not unlike running some sort of global virus or pandemic model. But what's nice about this is you can go down the rabbit hole, and this is an open source set of software code that's available. And they run it every day on the web. And so I live in Boulder, Colorado, and this is the state reproduction rate for Colorado over time. You can see in March, you started with a lockdown. When the shelter started, it was already dropping. And then when the shelter ended, the reproduction rate was below 1. So green is good, red is not so good. It rose in the middle of summer. They, sometime around the 4th of July, closed and limited hours in a lot of the bars in Colorado. And then sometime in the middle of August, all our university students went back. And our town in Boulder is about 20 to 30% university students in session. And lo and behold, our reproduction rate went back up. They actually locked down the students somewhere in here, and that drove the reproduction rate down. So this is being monitored on a continuous basis by the public health authorities. And how does this actually work? Well, you create this curve by basically saying the number of cases at some time is the number of cases at a previous time times the reproduction rate. And how do you calculate that? Well, it's essentially based on the testing rate. You take the number of positive tests, and then you adjust for a generation time of the virus and a transmission time, which is actually lagged based on the days before present. So this is just an example of how the model works. You basically, this is shown for Massachusetts. You take the test results. You have an expectation of positive test results, not by testing day, but by onset day. Then you smooth that out and you shift it. You correct it for the number of tests. So if you're testing more, you would expect to find more cases, but you can correct for that. And then you shift that based on this lag to the primary infections. And basically the change in rate of change of this curve gives you the reproduction rate from the infections at different times. And you actually then can derive it. So as you'll see, this has a lot of different parameters in it, a lot of different uncertainties, but it's interesting that that's how we actually model the virus, and that's how public health authorities are making some of these decisions. So now let's talk about uncertainty. And we're talking about, and that's what I want to finish up in the last section of this talk. When we talk about climate change, we want to understand how bad it's going to be. So for example, we'll ask questions like, what's the global average surface temperature in 2050? And we'll ask those questions of our models. The weather, we're looking at different things, and the weather models are actually very similar to climate models. It's just that where we put our effort on reducing uncertainty is different, which is what I'll get into. So you want to know what the weather is tomorrow, or you want to know what the weather is next week, or even what is the state of the atmosphere going to be in the next year, say with respect to, are we going to see a lot of hurricanes? Are we going to have an El Nino event? Things like that. Are we going to have a drought, or is it going to be rainy in particular regions of the world or in the United States? And for a pandemic, you want to know how many infections are we going to have in the US in the next period of time, whether it's the next week, whether it's the next month. And for example, you can ask more specific questions to couple these models, like how many ICU beds are we going to need in the next month? That requires coupling things like the virus model with public health outcomes. Well, climate and weather scientists definitely know something about prediction, and we know something about uncertainty. So let's talk about how we characterize uncertainty. So I'll go back to this. Plot of that I showed for Wisconsin and talking about the key uncertainties are actually different. So again, we talked about climate being the distribution, weather being the individual event. So for weather prediction, it's a short time horizon. You're pretty much looking at the next week, and most of the uncertainty about the weather tomorrow is based on the weather today, where you are, where this distribution actually finds you. So now this can always change, but if you're on one part of the distribution, the odds are you're going to be closer to that distribution unless you have a dramatic change in the weather, which is also possible, but that means the weather somewhere else affects the weather where you are. So the uncertainty for tomorrow is dependent on today, which is when you start your forecast. We call that the initial condition. For climate prediction, I could care less about the weather today because all I want to know is the entire distribution and how it's actually going to change. So the uncertainty in 50 years is different. One of the big uncertainties in 50 years is I don't know how much CO2 we're going to emit or fossil fuels we're going to emit into the atmosphere. I don't know what the structure of society looks like. So I don't really know how to be able to predict even what the basic state of the system is in certain ways. I have to use different tools for that. And my uncertainties come from different places. So there was a nice study by two scientists called Hawkins and Sutton that actually pulled this together. And if you look at the lead time for a forecast, so on one end, we're talking about the weather for short-term forecast, and on the other end, we're talking about climate for long-term forecast. There's a total amount of uncertainty. And what's interesting is that the total uncertainty is obviously we're trying to predict different things in space and time. So on the short end, we're trying to predict the weather in localized areas tomorrow. On the long end, we're trying to predict, say, the global average temperature or the regional precipitation in 50 years and how that'll change. So uncertainty goes up at both ends of that, and it comes from a variety of different components. One is this initial condition uncertainty. So the weather today depends on the weather tomorrow depends on the weather today. So it's very high. The uncertainty is dominated by the initial condition uncertainty. And then it drops over time to the point where it doesn't matter at all in 100 years what the initial conditions are today for the weather. I can start up my climate model at any point today, tomorrow, next week, and I get the same essentially global average mean temperature averaged over the planet, averaged over a year in 2050. The second piece of this is what we call model uncertainty. So these are the uncertain parameters. I don't know how many people actually tested positive for the virus. I don't know in a weather prediction model exactly how to describe my cloud with one term or two terms. And I don't know some of the difficulties in the individual physical processes in the model. That we call the model uncertainty. That's somewhat constant over time. It always affects the forecast. It always affects our forecast or prediction. And the third piece is scenario uncertainty. So this is how much CO2 ends up in the atmosphere. Or in the case of a virus and a pandemic, it's what's the intermixing among people. So what's the social distancing policies that are put in place? Again, so this is the weather and this is the climate side. And these things matter. So in a virus, also for viruses, it's very similar. It's a shorter time horizon, but if you want to know the number of cases in the United States in 2 months, well, that's very dependent on sort of what the scenario is, what public health authorities are doing. If you want to know them in the next week, it's actually more dependent on how many cases there are now and what the policies are right now, or they have been for the last 2 weeks. So again, the sources of uncertainty, and now I've got a little schematic. I'm going to try to keep the colors the same, showing this little plot of the total uncertainty, the scenario in red, modeling in blue, initial condition in green. So the initial condition uncertainty is what's the weather today, how many people are infected. The model uncertainty is how to represent clouds or how to represent the transmission of viruses, how infectious people are, how the physics of these drops actually work when people get together. And the scenario uncertainty are what are the emissions of CO2 or what social distancing or public health measures are put in place. Getting constraints from data is critical for a lot of these scales, both for understanding the processes and the transmission and for understanding the initial conditions, for example. The interesting hard part is for weather and climate, we know the small scale, we know the physics of drops, and we know the large scale, the global temperature, but we have a hard time describing at the large scale or in aggregate individual clouds and how they behave, maybe the 500 yards to couple mile scale. For viruses, we also know the small scale, which is the physics of drops and infections in bodies and disease outcomes. And we also know the large scale. We know death rates, hospitalizations rates. but it's snapshots for virus testing, and it's the small scale of how people, the intermediate scale of how people move around and interact that becomes very difficult to deal with in pandemics. So let me just show you some initial conditions. These are initial conditions for weather models. This is for June 2020. This is the observations that go into a weather forecast model. This one happens to be from the European Center model at ECMWF, and there's 125,000 observations that go in 6 hours. Basically, this is, and you see they're not distributed equally in space. There's a lot more of them over land, and there are a lot more of them in the denser populated regions over land than in sparser populated regions over land, and there are very few observations over the ocean. These are initial conditions for virus models. This is from June, and this is from Public Health England. You see the daily number of confirmed cases in England, so this can be used to generate and understand the R value. And then you can also look at changes in transport use if you're judging how your transmission works between different regimes. So this is by car, vehicles, rail, and transport, local transport in London, for example. The problem in weather forecasting, as I've told you, is initial condition uncertainty. And the way you get around that in weather forecasting and not knowing exactly what the current state of the atmosphere is, you run the model multiple times with slightly different initial conditions. This is the problem for weather forecasting. And the best way of understanding how to predict the weather is the errors in the initial condition propagate forward with physical laws. So if you don't know exactly the state of the world now, you won't know the state of the world in the future, and the spread will increase. So what you do is you take an observation, you perturb your initial conditions around the observation, you run the model multiple times, and you end up with, if you take your best guess, you end up with one particular result. But if you take all the different possible results from this initial state, you end up with a cloud of points. And that cloud of points is usually smaller than all the possible points in the climatology. So if we're thinking about Wisconsin in January, if you start today and run it forward for 3 days, there'll be a limited part of that distribution that is going to be the likelihood of getting a minimum temperature in 3 days. It's not going to be the whole distribution. And there'll be different probabilities that these will cluster in different ways. So that's how we make weather forecasts, is we use what's called ensemble weather forecasting, and ensemble being multiple sets of models. Well, you can do this for viruses too. This is an ensemble flu forecast. It was produced by Jeffrey Shaman's group, at Columbia University. And they take initial conditions. These are the past estimates of the total number of cases, influenza-like illness in a particular place. This is Salt Lake City for a particular year. And then they can project it forward with their virus model based on different assumptions about the initial conditions. They end up with very, very different trajectories in these simulations. And you can put all these different things, you can put lots of different model uncertainties also into this, and that's what I'll talk about next. So this horribly complex equation just shows the model uncertainty. This happens to be the cloud physics representation in one of our climate models. Each of these terms in here is a different physical process. These are for how rain forms. These are how drop sediment. This is melting, for example. This is condensation. This is a description of terms. They each have uncertainties associated with them. And what we actually do is we want to actually get constraints on these terms from observations. Well, how do we do that? We can train these things on the past, and that's what's been done. This is the virus model equations I showed you. And again, all these terms for virus models, some of these things are observed, the number of tests, the number of positive tests, but some of them actually have to be parameterized. And parameterized means we have to estimate these numbers based on constraining it or limiting it, training the model on observations. So and some of this is based on physics, and some of it is based on public health or observations. So for example, there's a generation time or a transmission rate, there's an onset delay, and there's the number of days infectious. And you can see this is actually generally, we generally find this and describe this when we get to we develop these things based on data. The last one is scenario uncertainty. And the scenario uncertainty is how the future is going to evolve. The future typically depends on human policies that are outside the models. We run ensembles not just of individual initial conditions, but when we're looking at long-term projections, we actually want to run ensembles of different scenarios for either virus or climate models. So on the left is an example from Jeffrey Shaman's group for running a COVID model. This was run sometime in late March during lockdown. And this is what public health authorities were using to say, well, we need to lock down because if you don't have any control measures, it's going to look like this. We'll see 500,000 cases a day. If you put in some control measures, it'll go down. If you put in more severe control measures, you'll actually get very, very low rates of transmission. So these are predictions that are made that people use to actually make decisions. And they basically are adjusting not the model. The model is the same and the initial conditions are the same. They're actually adjusting what goes into the model in terms of these scenarios for, in this case, social distancing and how people interact. So they're affecting the transmission rate when they do this. So you may have seen plots like this. This is actually the global average surface temperature, and these red line over time. The gray is the historical. The spread is estimates from 30 different climate models. And then the future is 2 different scenarios. And this is the global average change in temperature. And this tells us something actually interesting. This tells us by about 2050 that the climate of the future, the spread in the models, the model uncertainty is this part of the curve, the shaded area. But the model uncertainty is smaller than the scenario uncertainty when we pass 2050. That actually means the climate of the future is our choice. We get to pick whether we're going to be inside of this shaded region, the red one or the blue one. And that's a function of what we choose to put into the atmosphere. That's not something climate models predict. It's something that society chooses to do. And it's a function of policies that we put in place. So let's finish up and try to bring all this together. The goal of this is to understand for the different scenarios how much pollution we should be allowed or how much social interaction we should be allowed that might spread the virus. So the physics and biology are constant. We have a bottom-up cloud and aerosol physics for both looking at viruses and looking at climate change. And for viruses, we also then have the viability and the comorbidities that result in understanding public health outcomes. Public health provides a macro picture. It provides testing rates. This is like an energy budget model of the planet, or observations of the planet from space, which provide a current state of the system and say, what is the total energy on the planet? It's a macro picture, it's a snapshot. These scenarios are critical. How much carbon dioxide do we emit, or what policies affect the transmission rate for a virus? And what you see is we have this real-time application of scenario uncertainty to critical policy decisions. So if we're talking about we want to keep the planet to 1.5 or 2 degrees of warming, how much CO2 can we emit? The flip side of that for viruses is, do we keep the bars open or not? How many cases are we going to end up with? So this reproductive number for viruses is a function of these different types of uncertainty. It's the initial conditions, it's testing, it's the model uncertainty, the transmission or reproduction rate, and it's the scenario uncertainty, the policies that modify social distancing. So coming to the summary, the virus spreads by talking and breathing. Masks help. We understand that from the physics of the problem. We do need more interesting work at the intersection of aerosols and viruses. There's a lot of expertise in our community, but not on dealing with viruses. And there's a lot of expertise at dealing with viruses in the medical community, but there's very few people working at this intersection. Our world was turned upside down and people stopped moving, and our air was temporarily cleaner, except for wildfires. But that only modestly affected climate, for example. Stopping transport's not really the issue. Renewables are benefiting though, and we may see some lasting positive impacts of this. And there may actually have been a slight warming from reducing basically these aerosols or the pollution that would offset changes or reductions in the greenhouse gases or fossil fuels. So finally, how do we predict the future and where are the sources of uncertainty? Well, it's useful to think about this in any modeling framework. There's initial condition uncertainty, model uncertainty, and scenario uncertainty. And minimizing uncertainty depends on when you want to do your prediction. And it also provides some policy guidance. For the virus, it provides policy guidance about increasing testing, reduces your uncertainty in the near term. That's sort of the weather part of the problem. And the scenario, it also putting in social distancing effects and looking at the ideas of changing the scenario and the transmission rate can actually tell us a lot about future public health outcomes in the same way we do that for climate change. So hopefully giving you an overview of how some of the impacts of these intersections, these 2 global interconnected and very difficult problems that go to the fabric of our lives. I think there's some positive messages for how we understand uncertainty, how we can actually predict the future, and that this has had some impacts on climate, that it's shown us a few things about climate that I think will help policymakers. And it probably long-term has led to a few benefits in showing us how some of these other energy choices and other energy systems are actually very useful. And I think I'll just stop there.
Great, thanks so much, Andrew. Just a reminder for folks, if you have questions you want to ask, please put them in the Q&A box. And we have a couple for you already. So one asks if you could remind us how you calculate or predict the model uncertainty.
Okay, so there's a couple different ways of the model uncertainty. We typically look at model uncertainty by what we call hindcasting. So we run the model in the past where we actually know the result. So this is commonly done in weather prediction, where instead of running you run a forecast, but you run it from last year and you run it forward for a week. And if you do that, you look at your forecasts and you see how they failed, and you try to improve your model and see if you can make those failures go down. And the same thing is done with virus models. Sometimes these are actually used to train the model, where you adjust the uncertain parameters in the model. Like things like the transmission rate can be trained on past data for infections over time in particular regions. And sometimes it's done by actually comparing, you can reduce it by comparing to observations. So it's a multifaceted process where we use all the tools available to try to understand how do we reduce our model, where our model uncertainty is, and how we reduce it.
Thanks, Andrew. Here's a question, not sure if you'll be able to answer this or not, but it's about flu forecasts.
Okay.
And the question is, can you talk about the uncertainty included in the posterior part of that flu forecast? So the posterior, and what does that indicate?
Right. So the posterior is uncertainty that goes into the forecast, and that's based on two things. That's based on uncertainty in knowing the number of people infected, and it's also based on adjusting these model parameters to try to fit to data. So in this one, they sometimes do this in weather modeling as well. You actually, for your different ensemble members, you can also vary the forecast. You can vary the model parameters. So you can have a slightly different model, not just a slightly different initial condition. And that's what this is. This is a more complicated way. And what's interesting is this group has people that have worked on weather prediction. So a lot of the tools they've used to build these flu-like models, and they're now using on COVID models, this is the Columbia University model, have come out of understanding of how we do uncertainty with weather prediction.
So here's a philosophical question for you, Andrew. Of all the lessons learned you sort of had there on the end slide, is there something that you think is the most important takeaway for the general public?
The most important takeaway for the general public, I think it's the two things are that it's interesting that to look at climate change. At climate change is just a very slow pandemic that requires us to actually have fundamental changes for how we do business and how our lives evolve. I don't think we need to. The advantage is changing your life slowly is a lot easier than changing your life very quickly. I think the other thing it's taught us is I think the climate effects of the pandemic were minimal in the short term, but we've learned some things about our energy system. We learned some things about what we really need to do every day that may inform us about some of the policy choices we want to make for climate change.
Thanks, Andrew. Here's another one about COVID modeling.
Right.
What kinds of COVID modeling aren't currently being done that could have the biggest impact on getting us out of this pandemic?
Oh, okay. So my thought is the biggest thing we missed was using the opportunity for big data to actually tell us things at the aggregated level. And that was, they've done this in a limited way, but one way people have heard about these testing and tracing apps. Well, one way is to actually use them to say, okay, well, let's put it on everybody's phone and see when people were interacting and try to trace back individual infections. That has privacy issues that people haven't really liked, and the testing and tracing human aspects of that have been very difficult. Plus, there's uncertainty with how close people actually are. But if you had done that, and there's a couple places where they have, and just anonymized all the data, you could actually see statistically where the infections were actually happening at a high level. You could see where the clusters were happening and just how individual elements and locations were actually transmitting the virus, even if you made it totally anonymous. And you could ask questions, okay, well, where is the spread occurring? Do we think it's occurring in bars? Do we think it's occurring in schools? How do we act? Do we think it's occurring on public transport or not? I think that could be used to back up some of the physics of the problem that we've done. And then I think there's not enough knowledge of, we can understand how viruses happen in the air, and we understand how these particles persist, but we don't really know the details of how viable the virus is and how people get infected. What particles infect people the most? I think that's the other part of it.
So with that big data information, would that help you then reduce some of, say, the scenario uncertainty in modeling? Because now you know, oh, it's all bars and not schools.
Right. You could actually refine your transmission rates, and you could define your scenario uncertainty by saying, if I close the bars, I expect infections would go down by this, the transmission rate would be reduced by this amount. I think that's a real missed opportunity that people just didn't see. We have these amazing techniques from artificial intelligence or machine learning to sort through these large data sets. And we have the ability, with everybody carrying around a phone, to look at all this just general position data.
So
but there's obviously privacy reasons why people wouldn't want to do that. So we haven't.
There's another question here about scenario uncertainty, though, which is, would scenario uncertainty also depend on initial conditions chosen? Meaning, is there an interplay between initial uncertainty and scenario uncertainty?
There is in the medium term. So for virus modeling, there obviously is, because we're looking a month or two in advance, and that's only a couple of virus replication times. For climate modeling, it doesn't. So the estate of El Nino now doesn't affect the climate in 50 years. If you wanted to know what's the pandemic going to be in 6 months, then actually the initial conditions don't matter as much either. It's a function of the lead time relative to the sort of evolution time, turnover time for the atmosphere, or a couple of turnover times of sort of a virus transmission chain.
So back to another COVID-19 model question. So in discussing COVID-19 models, you mostly talked about R, while recent research has suggested that K, measuring the virus's dispersal, might be more useful. How does this variable compare to R in how it is used in models, and the uncertainty we should consider when thinking about that? I don't know if that's too big of a virus question for you, but.
So dispersal, I mean, you can think of this as being a chain of things. So first you have dispersal, then you have, and that factors into the transmission rate, and the transmission rate factors into the reproduction rate. So it's a piece of the chain. I don't know which one is actually more important. You can affect different parts of the chain with different social policies. So if you're thinking about dispersal rate, that's masks. If you're thinking about transmission rate, that might be social distancing, or what you allow to be open. So they're actually different pieces of the same sort of problem. You can almost think of as multiplying together in some way to create an uncertainty. So I don't know. I would defer to experts in epidemiology about which is more important.
So a question on, do you have thoughts on what we've learned about the pandemic that can help with climate crisis when it comes to changing human behavior? And I sort of had this question too, like, should I stop feeling guilty about flying on planes, or does individual behavior matter, or is it just source pollution? And
I guess, I mean, that is, so should I not feel bad about flying on planes? That's a very interesting one, because I've talked with a lot of people about that, particularly in Europe, who really got upset when I stated that, because it is individual behavior, but we have to actually focus on what's the most important. And I think what we've learned is everybody has to make a small choice every day in order to solve some of these big societal problems. With climate change, it's an easier choice because we can be nudged slowly, but it has to happen at both the macro level and the micro level. And maybe that's the message. Part of it is people have to buy into the solutions, is the other one. If people are unwilling to buy into the solutions, they don't do what we want them to do. It doesn't work. You don't get the policies in place. So I think those are the two major messages. It's both a top-down and a bottom-up thing. You have to have the right policy choices, but there has to be support for those policy choices. For climate change, I think it's easier because you can use economics in a way that's harder on a short-term public health outcome. It's not like you can get people to stop traveling by just you don't want to do it by just raising the price of plane tickets, in the same way that you could raise the price of fossil fuel emissions and actually reduce the use of fossil fuels with things like taxes or incentives that way.
And it seems like you're battling a bit too the same with the pandemic of who do you trust? How do you trust scientists? What talking heads, to take that action?
Well, it's also uncertainty and impacts. And I haven't talked about looking at uncertainty and impacts with respect to climate. Obviously, and we haven't talked about, I've only vaguely talked about uncertainty and impacts because nobody gets killed by the global average mean temperature, right? In the same way that the total number of cases doesn't tell you the total number of deaths. You have to know a lot of other things to get to that impact point. And so it really is focusing on the impacts for people and the timescale for that. But it's a great question.
This is a question that comes back to that slide that maybe surprised a bunch of folks about. One side effect of clean air is warmer surface temperatures, at least in the short term. And so this question is it correct to assume that if cleaner air becomes the norm, the associated warming would be minor compared to the warming associated with more greenhouse gas emissions?
It is less. It is a fraction, but it's maybe 20 or 30%. The other thing that we study as scientists is one of the problems is all the pollution is offset greenhouse gas emissions. And because we don't really know the impact of the pollution, it makes it hard for us to determine from observations what the total human effect on the planet is. We assume we're going to be cleaning up the air because we have to do that. Gabby's going to talk a lot about that. That's a great segue. But it does mean a slight increase in the potential for climate change. That is factored into most of our models now. And part of it is the time scale. That warming from pollution, because pollution only lasts for a week, is immediate, whereas the effects of carbon dioxide are averaged over a much longer period of time.
Here's a question that says, I saw an article about genomic modeling of the virus and how that could help us fight it. How would that work? I'm not sure if you'll know that one.
I don't know the answer to that. I mean, the genomic modeling tells us where the strains come from. So it tells us where people have different aspects of the virus. If it's getting into the mutations of it, that part I don't really understand. I'm not an expert on.
So another question you mentioned sort of earlier, at the very beginning, you were talking about size of droplets. And you said, we could take one of our cloud droplet measuring instruments off an airplane and then cough on it, right? But that would be one piece of the puzzle you need to work with the epidemiologists about viruses and how they survive and that kind of thing. Do you foresee opportunities in the future that atmospheric scientists and epidemiologists might work more closely together? Or do you feel like science is sort of doomed to stay in their own towers? Or where do you see that going?
I do see it coming together. I think there's a lot of different potential intersections, both in the science too. I mean, some of the groups that we've talked to, like the group at Columbia, they actually have background in, and some of these models actually include either weather or other things in them, because if the weather changes, people are inside or outside more, and some of the flu transmission models actually include some aspects of weather in them. But I do think there's a lot more opportunity for us when things calm down and we're not in the middle of a pandemic to try to work together on some of the spread of drops. Interestingly, the aerosol thing has been a big issue in the public health community because for historical reasons, they haven't wanted to really deal with the fact that the air itself could be hazardous. That's really scary for people. And that was something they tried to debunk in the early part of the 20th century for a long period of time. So there's been actually resistance in the public health community to say that aerosols are a big part of the problem. But it's kind of hard to ignore. And a lot of the aerosol scientists have been saying that since the first, say, month or two of the pandemic in ways that's why things like masks and doing things outside actually really make a difference.
So I think we have time to squeeze in one more, Andrew. This question says, has there been any research on the coronavirus being detected on particles of air pollution? And do you think that's something that should be considered?
There was some early work on that. It has been considered, but all it did was find bits of virus RNA on air pollution particles that were transmitted. It may be that air pollution can provide a place for the virus to stick and it actually promotes the transmission of it, but that's probably outside and it's probably minimal. And there hasn't been any follow-up work showing that the virus on those particles is actually viable. The chemistry of those dry particles is not very conducive to biological material. It would tend to break up biological material. So they found pieces of the virus in northern Italy on air pollution particles, but it's not clear that was viable. It's just pieces of the virus RNA, basically. So there hasn't been a lot of work showing that that's a real solid transmission pathway. That's very speculative.
Okay, well, Andrew, thank you so much for your time today. And thank everyone who was able to join us. And hopefully some of you will be able to make it to our session here in half an hour on air pollution and COVID. And thanks for hosting us to CASW.
Yes,
thanks, everyone.
Thanks for your time.